Welcome to day 7 of our low level design course. Today, we dive into one of the most essential but often overlooked areas of software design, error handling and exception management. When systems grow in complexity, so does the number of things that can go wrong. From user input errors to third party service failures and internal bugs, exceptions are inevitable. But with proper design strategies, we can ensure our applications fail gracefully, remain maintainable, and deliver a reliable experience to users. Let's explore how to design error handling flows that are both thoughtful and robust. Why do we focus so much on error handling? The answer is simple. Failures are a given in any real world system. Whether it's a null pointer, a network call that times out, or a user submitting invalid data, systems must be able to handle these gracefully. Good error handling allows for quick diagnosis and recovery. It supports testability by exposing clear paths of failure, and most importantly, it enhances user experience by providing meaningful feedback rather than cryptic code errors or application crashes. So, error handling isn't just defensive programming, it's a cornerstone of thoughtful software design. Errors can generally be divided into three types. First, we have compile time errors. These are caught during development, like syntax mistakes or missing method implementations, and are relatively easy to fix because they are flagged by the compiler. Next, we encounter runtime errors. These slip past the compiler and emerge only when the program runs. For example, accessing a null object or dividing by zero. Lastly, there are logical errors. These are the most dangerous because your code runs without crashing, but it produces incorrect results, perhaps due to a flawed algorithm or incorrect assumption. As designers, it's crucial we understand these types so we can build systems that detect, isolate, and recover from them effectively. In many statically typed languages like Java, exceptions are categorized as either checked or unchecked. Checked exceptions must be explicitly declared and handled. This represents recoverable situations like a missing file or a failed database connection. You can anticipate them and design fallback behavior. Unchecked exceptions, on the other hand, indicate bugs in the program, such as null pointer dereference or an illegal argument. These are typically caused by programming errors, and while you might catch them, it's often better to fix the root cause. This classification helps us distinguish between predictable system failures and unintentional code defects. Let's look at some proven best practices in designing exception flows. First, fail fast. If something is wrong, don't delay detection. Raise errors early and clearly. Second, never swallow exceptions silently. Always log them with enough context so developers can debug easily. Third, use custom exceptions to represent business level errors. They provide clarity and intent. Avoid generic catch all blocks unless you are at a very high level, like an error boundary. And finally, always log with relevant context such as input, user session, or timestamp. These practices improve observability, simplify debugging, and lead to better system behavior over time. Where you handle exceptions in your system matters a lot. Should the service layer handle them or should the controller? A good pattern is to let lower layers throw exceptions upward and handle them centrally in a top level layer like a controller or global middleware. This avoids cluttering your business logic with try-catch blocks. In microservices, centralized handlers ensure consistent error responses. Also design retry logic wisely, especially when calling external services, and always have fallback mechanism in place, like showing cached data if live data isn't available. These patterns ensure systems degrade gracefully under pressure. Custom exceptions are powerful tools. Rather than using generic exception classes, define domain-specific ones that explain exactly what went wrong. In this example, product out of stock exception extends runtime exception and clearly states which product ID failed due to being out of stock. This makes your error logs, exception handlers, and business rules more expressive. It also encourages developers to think in terms of the domain, not just technical failures. Well-named exceptions act like documentation. They explain your design decisions without comments. In real-world systems, centralizing your exception handling is a huge win. Frameworks like Spring Boot offer tools like REST controller advice to catch exceptions across your entire application. In this snippet, we define a global handler for our product out of stock exception. We return a clear HTTP status and a message ensuring clients receive consistent responses. Centralization also makes it easier to implement features like logging, notifications, or altering. By separating exception handling from business logic, we keep our code clean, testable, and scalable. Now let's put these ideas into practice. Your task is to build an error handling module for an online shopping cart. Define at least three custom exceptions, perhaps for inventory issues, invalid payment methods, or expired discount codes. Handle them in your service layer with clear logging. Implement a centralized exception handler to format your error responses. Bonus, add retry logic for your payment gateway. This exercise brings together everything we have learned today and gives us a real taste of designing for reliability. Let's highlight some common mistakes. First, avoid catching exceptions or throwable unless absolutely necessary. It hides the true cause and makes debugging harder. Second, don't suppress exceptions silently. If an error happens and you don't log or report it, you are setting yourself up for disaster. Third, never use exception to control flow. It's inefficient and confusing. And finally, be mindful of thread level failures in concurrent systems. Just because your main thread is running doesn't mean background tasks are. Always have a strategy for thread exceptions propagation. Let's quickly review what's the difference between checked and unchecked exceptions. Why should you bother creating custom exceptions? And what's the danger in catching all exceptions without discrimination? These questions will help reinforce our understanding. Take a moment to reflect or discuss them with peers. It's a great way to internalize today's material. Before moving on, be sure to complete your deliverables for today. First, implement three custom exception classes that represent real business scenarios. Second, draw an exception flow diagram to visualize where and how errors propagate through your system. And third, write a centralized handler that ties everything together. This will not only help you grasp today's concepts, but will also serve as valuable building blocks for your final capstone project. Thank you for your attention.